This video is going to narrate the solutions to our two FRQs that we have here that involve capacitors that have modifications made to them, or if multiple capacitors as we see in this first problem. So you can see as this first circuit shows there are two switches, and in the text here it's going to tell us that we're closing switch 1 and opening switch 2, which is actually how it's appearing here. So this branch that's on the right here is not part of the problem right now because it doesn't have a closed loop. So we're only looking at this first loop here as having the closed loop. Immediately this is going to have a capacitor voltage of 2000 according to loop rule. So it's going to have immediate charge because there's no resistor in this circuit. So it's not an RC circuit, it's just immediate charge. So these first two are pretty easy in terms of how straightforward they are. You know, we're just going to be solving for the charge and the energy. Let's move into the more advanced problems with this. So it's saying now at a later time we're going to open switch 1, which disconnects it from the battery, and then we're going to close that secondary loop to the right by closing S2, and I've drawn that below. So we have that two capacitors are going to now be connected to each other. Now the capacitor on the right does not have any charge initially on it. The capacitor on the left was already charged from our previous part A. Okay, so it wants to get the initial current through the resistor, this 1 mega ohm resistor on the top, immediately after the switch 2 is closed. So in this case, what I was trying to say there is we're going to apply loop rule immediately, right? Loop rule is going to be the primary concept that we're going to apply to all circuits whenever we are looking at stuff. And so that tells us voltages. So the voltage across the capacitor, which I'm going to call 2, it's the one that has the 2 microfarad, the voltage was initially 2000. So that's going to be immediately what it is as soon as we throw that switch. Okay, and then there would be a voltage across resistor if there's current flowing, and then there'd be voltage across the capacitor that I'm calling VC6, and that would be the 6 microfarad capacitor. Now I put down that that charge initially is 0 because it's initially uncharged, so it has no voltage dropped across it. That would mean that that 2000 has to be dropped across the resistor, which would imply there has to be current flowing, as you see here. So the idea is that we have a lot of voltage here due to the charge. We have an uncharged capacitor here, so it's going to start to give charges over to that uncharged capacitor until they reach the same voltage, right? And that would mean what I have here in orange, they are in equilibrium. There's no voltage gradient between them that would cause flow from high to low. So right now it's high versus 0, right? High voltage here versus no voltage. So it's going to start to throw charges over to it. And when charges move over to it, it creates current, and that's what we're calculating right here. Now that current's going to change as the charges on this capacitor start to accumulate over time. And eventually it will be no current through the capacitor once we reach its steady state full charge. Okay, now that equilibrium has been reached for a long time, we're going to determine the charge on the positive plates of each of the capacitors when it is at what we call equilibrium. Equilibrium is defined as having the same voltage across both of those. This is really just loop rule when there's no current flowing anymore. So there's no voltage loss across the resistor because there's no current flowing through the resistor. One of the hard parts about this problem is recognizing that although we have two unknowns, so we're going to need two situations here. The driving factor would be the same voltage, but this is the one that may not be as easy for you to realize right off the top. So what I'm saying here is that the initial charge on capacitor on the left, right, that we start off with, that charge is going to then be split. Some of it's going to stay on the 2 microfarad capacitor, and the other is going to go to the 6 microfarad capacitor. So the initial Q naught on the single capacitor is now going to be split between the two, and so we have a conservation of charge concept here. And so I got to figure out how much splits, and I'm going to use the proportions defined by them having the same voltage. And so using this equation that relates voltage, charge, and capacitance, and the concept that they have the same voltage because they're in equilibrium, I can then set up the proportions of what Q2 to QC would be. And knowing that these have to add up to Q naught, I can get those charges. So that was a tricky one on this one. So hopefully now that I explained that, you're seeing that a lot of this stuff is using proportional reasoning and just variations of those circuit laws like loop rule and V equals Q over C, V equals R, etc. Part D is asking now for the total electrical energy in the two capacitors when at equilibrium. So this should just be a 1/2 CV squared. Like sub and solve, we just need to get the voltages first if we're going to use this equation that has the voltages. You could also use other equations like the one that has Q and C in it instead. There's a couple of variations of this equation. And one of them is on your equation sheet. We've talked about how there's a couple of different versions depending on if you want the potential energy written in terms of like C and V like this, or Q and C, or V and Q. All right, so moving on to then the second problem. This looks like a simple RC circuit, but it's going to have a modification made to it. In this case, it's going to increase the spacing. These plates are going to be pulled apart. So pretty simple setup here. Determine the energy stored in the capacitor when it's fully charged. We go right to loop rule to get the voltage at steady state. And in this case, since it wants energy, we know we got to use that sub and solve energy of a capacitor equation. And we get to the harder part here, which is going to say that the spacing between the capacitors is suddenly increased. So it's going to mean it's instantaneous. It has not had any time to change the charge. It hasn't had any time to reach that exponential flat line that we call steady state. So in that case, then, we're going to be, first of all, figuring out, okay, by increasing the spacing, that's going to decrease the capacitance, right, like we've done. That's by a factor of 4. Now, work done, I'm going to do indirectly by just saying, well, what's the change in energy for the capacitor? I already got what it was originally in part A, and so now I can figure out what would happen then to C and V that would change the overall energy in the capacitor. And I'd recognize that it's going to end up with a higher amount, so it's going to be positive. It's going to be work done that, depending on if it's done by the field or done by the agent, that would be gained or lost. In this case, the capacitor itself is going to be gaining energy. We can loop rule this as well, and so we know the battery voltage that we have is going to also drop then across the resistor because we have 4 times the battery's voltage across the capacitor. So let's take a look really quick at where this 4E came from and how we knew that there was voltage across the resistor. So when I was writing this up, I just wrote out all the possibilities. We had voltage across the resistor, voltage across the capacitor, and then I looked at this idea that if I'm decreasing the capacitance and charge has not had a chance to be removed or added on, then it's going to initially be the same because it hasn't had a chance to react to us increasing the spacing. But since there was work being done, that is instantaneous, and that's going to then increase the voltage in the capacitor by a factor of 4. That means it's going to be 4 times the voltage across the battery with that added energy from us increasing the spacing. That would mean that we're going to end up having to have 3E sorry about the jump. Took away my magic that I was planning. So that's going to be a positive 3E. That's going to imply, because it's positive, that the current is going to go back towards the battery, as opposed to if it were negative, that would mean it's coming from the battery. And this is just at the instant that we turn the switch, right? So since there's a voltage across the resistance of 3E, that's going to have a current, and we could figure out that current if we wanted to. It's not asked in this particular problem for B. Part C, then, it does say what is the current in that. So I've already got the legwork done, and if I plug in number values, we're going from 20 volts. That means there's 80 volts dropped across the capacitor, which means there's got to be 60 volts going backwards. That would be counterclockwise in the diagram. Back to the battery as it discharges off some of that charge. The capacitor is discharging off some of that charge. And that current is going to create a voltage through the resistor of 60. We can use V equals IR to get that current. This wants to know how much total charge is passed through the battery. We could figure out how much charge is given off by the capacitor, and that's what's being sent back to the battery. And we could also figure out then, based on that charge that's being sent through the battery, how much energy is being added back to the battery. The wording of these D and E, I felt like, makes it a little bit confusing, but once you get through it, it's pretty straightforward, I hope. All right. I hope that clears things up. Thanks.